Check, check. Perfect. Lydia, ready? Lydia, is it good? Perfect. All right. Good. Welcome, everyone. The 8th lecture, I guess, of the Advanced Topics course. I'm going to pick up where I left off during the time I was supposed to give you on lunch break, last lecture. So we had just discussed protocols for erasure, and in doing so, we discussed how we can actually saturate the Landau's principle. So by the way, I didn't actually use the word Landau's principle for some reason last time, but the inequality we got in the Maxwell's demons lecture, where we said, well, we need to dissipate a certain amount of heat in order to erase some information, that is commonly referred to as Landau's principle. So yeah, so we discussed erasure protocols and we got results. But now what I wanted to do, what I started in the last lecture, was discussing what happens when we do erasure, when the system we want to erase is actually possibly correlated with another system, and we do have access to that. So we have two systems. We have the system of interest to us, which I call S, and another ancilla, I'm going to call it A. And the state of A is actually not important to us. We can leave it in the worst state we like. The state of S is the one that's important to us. We want to have it end up in the state 0, because for erasure, we want to end up with the system in a pure state. And so I gave you these 3 examples. We have 3 different density matrices for the system and ancilla. One of them is just the product of maximally mixed states. The second one is a correlated state. If S is in 0, so is the ancilla. And the same thing if they can both be in 0, both be in 1. And the third was a maximally entangled, one of the Bell states, phi plus phi plus. And just as a reference, phi plus is superposition of 0, 0, and 1, 1. Okay, and importantly, in every one of these 3 cases, the system itself, if you look at just the reduced state of the system, it is the maximally mixed state. So if we were not looking at the ancilla, if the ancilla was not available to us, then erasure would be identical on all 3 cases. But having access to A, we can do something interesting. And that's the question, could we perform a good unitary operation on the system and ancilla together that will help us in the process of erasure? And the reason that this is important is, now what I'm going to do is I'm going to look at the entropies in each of the 3 cases. In the case of row 1, I have that the entropy of the system is 1 bit. The entropy of the ancilla is also 1 bit. So this is now 1. And the entropy of the system and ancilla is 2 bits. It's a product state, so this is as expected. In the second case, the entropy of the system is 1 bit. The entropy of the ancilla is also 1 bit, because if we trace, this is a symmetric state with S and A, so if we trace out S instead, we would get again the maximally mixed state for A. But the entropy of S and A together is also, in fact, 1 bit, because it's just a mixture of 2 states, right? And in the third case, the entropy of S is 1 bit. The entropy of A is 1 bit. Again, if we take the maximally entangled state and we trace out any of its subsystems, we are going to get the maximally mixed state as a marginal. But the entropy of the joint is 0, because it's a pure state. So clearly, now the whole point of erasure is actually to decrease entropy. We start with a maximally mixed state and we end up with a pure state. But there's something different about these three cases. In the first case, there's nothing really we can do. We start with the maximum possible entropy, so we're going to have to do erasure. But in the second case, the total entropy is 1 bit. So the easiest thing that we could do is to say, well, can we concentrate the entropy that is currently on the whole joint system and sort of hidden in these correlations? Can we concentrate it just on the ancilla so that our system is pure? And that is absolutely the case. So we do the following unitary. And I'm going to just write the unitary as a state conversion. So 0, 0 just goes to 0, 0. 1, 1, and these are the two important ones, goes to 0, 1. And then the other two can do anything. So 0, 1 goes to 1, 1, because these two switch, and 1, 0 remains unchanged. Okay. And what do we get from here? We get that rho prime 2, I'm going to call it. So when we do that unitary on this, the 0, 0 state remains unchanged, but the 1, 1 state changes to 0, 1. So we get 0, 0, 0, 0 plus 0, 1, 0, 1 by 2, which is 0 on the system, tensor identity on the ancilla by 2. And this is a state that, with respect to the system, is already erased. The system is already in the state that you want. And so by just doing the unitary and concentrating the joint entropy of everything just on the ancilla, we were able to essentially get erasure for no cost at all. So at this point, you should be able to suspect what's coming. In the third case, then, I can do a similar trick to erase the system. So in the third case, for when it's a Bell state, I now know what I want to do. I want to get 0 on the system. So I just do U is, I rotate the Bell basis to the computational basis. And so this will do, for starters, it will do phi plus goes to, let's say, 0, 0. And then the rest can do anything. Phi minus can go to 0, 1, dot, dot, dot. It doesn't matter. We just complete the unitary any way we want. And at the end, we're going to get that rho 3 is just 0, 0 tends to 0, 0. It's a pure state of the system and the ancilla. So of course, we've managed to erase the system. But now there's something more we can do. You see in the first and the second case, when we do erasure on the system, the ancilla is left in the maximally mixed state. So in the first case, we don't touch the ancilla. We only do stuff in the system. In the second case, first we do this unitary, leaving the ancilla in the maximally mixed state. Then we have what we want. But in the third case here, the ancilla is in a pure state. And because we don't care about the state, we can use it as a resource. So now we do work extraction. And we get rho 3 prime is equal to 0, 0 on the system, tensor identity on the ancilla. And the result of this is that the work here, the work of erasure inverted commas, because we didn't need to do erasure, is actually minus KT log 2. So in the first case, I didn't write this down, I should. So in case 1, W was equal to KT log 2. In case 2, W is equal to 0. And in case 3, W is equal to minus KT log 2. Okay, is there any question? So using the, let me set this up. So now I'm going to state a result, and we're not going to prove it in generality, but it is a useful result. And this is about erasure with side correlations. So one thing you can notice when I write all of those entropies out is a useful quantity sort of encodes what's going on, and that is the conditional entropy, which is defined as H of let's say system given ancilla is equal to H system ancilla. Oh, well, this is now H entropy. have written. So H system ancilla minus H of the ancilla. And you can see now in the three cases, in case one, the conditional entropy was actually equal to 1 bit. In case two, the conditional entropy was equal to 0. And in case three, the conditional entropy was equal to minus 1 bit. This is something that is particularly quantum. The conditional entropy can in fact be negative. Yes, and it's not a coincidence that the work that we extracted came out to be that. And so here's a general statement. If we have actually a system and an ancilla, which start off in a joint state, then the work cost of erasure for the process. And now there are two cases here. The first case is the asymptotic case. So in the asymptotic case, when we consider asymptotic results or ensemble results somehow, or I can also say it as ensemble, what it means is that rather than having a single copy of the state of rho of the system and ancilla, I have many copies n, and I can do a procedure on all of them. So I can do the unitary on all of them together, and then I can do the erasure protocols, of course, on each of the systems. And whatever result I get, then I divide it by n. So this is somehow the average work cost if I processed n at a time. And when you get that, when you have n copies and where n can be as large as you like, then in fact you really get that it is equal to h of s given a at log 2, or it approaches that. So it's always that plus a small inefficiency, but this, as you know, we can get. But this, you know, from the last lecture, we can get to be as small as we like by simply taking our erasure protocol to be more and more complex and have more and more steps. In the single shot case, I will not actually write the precise result, but simply say that W is related to, there is a quantity here that involves H epsilon max, S given A. And this is I don't know whether you did single shot smooth entropies in AT, you did in, okay, so those from the AT-QIT, not AT-QIT, the QIT lecture will recognize this. So this is the smooth max entropy. And this is exactly what you need when you're considering protocols that really do a single shot version of action rather than something on an ensemble. So it has a property that when you have n copies of a system, as n tends to infinity, it tends to the von Neumann entropy, which is why you have the asymptotic result. But when you have a single shot case, you have this. And this is a more complicated result. You have the result that W is equal to this with a small probability of failure. Which depends on epsilon. All right. So this is something that is not in last year's lecture notes, but when I get to updating this after I finish my part of the course, in that section I will provide references for the paper. In fact, the paper is one that was written by Lydia and other co-authors at ETH Zurich, 2011, I think. Yes. Perfect. All right. Now let me erase. Are there any questions? Nope. All right. right, and for the second part of this lecture, so one of the things you will have noticed, or at least which is true about the course so far, is that I've stuck to what I would call incoherent operations. I define the notion of coherent states and incoherent states, which basically differ as to whether the state has an off-diagonal element in its density matrix between two different energy levels of a different energy eigenvalue. And all of the protocols, the simple qubit swap, and the protocol that I did yesterday, Erasure, none of them actually introduced any coherence into the state. So even in the case of Erasure, though I was doing a unitary that involved different energy levels, they simply swapped it fully. So you could imagine this as a special case of a rotation between these two levels. But here I just did the 180 rotation. So I left if the density matrix starts with no off-diagonal element, the resultant unitary also did not introduce an off-diagonal element. I mean, the same thing when we put the work source yesterday, there was no coherence introduced. The work source itself that I defined yesterday had coherence, but there was no coherence introduced. And so now we will discuss shortly what is the way that we can actually manipulate coherence in quantum thermodynamics. And I'm going to do one simple example that will essentially show what the features in the general case are. So it's a very simple example. I have now a system S. So S is a qubit. And HS is 1, 1. So this is a qubit which has an energy gap E between the ground and excited state. And all I want to do is I want to take psi S, which starts out in 0, starts out in the state 0. I want to take it to psi prime S, which is 0 plus 1 upon square root of 2. So the plus state on S. Okay, now this is clearly involving coherence because I start out in an energy eigenstate, but I go to a superposition of energy eigenstates. Okay, so I want to be able to do this, but the important part now is I want to be able to do this with an energy preserving operation. Okay. And explicit work storage. Because, of course, if I just write down these two states, you can tell me, well, I know what the unitary is. I just write the unitary that takes 0 to plus, and I'm done. So there's no big deal in writing down the unitary. But in thermodynamics, we want to take into account where we get the energy from, where the coherence that is required to manipulate this comes from. And so what I want to do at the end is I want to include whatever I need for this unitary inside in such a way that the end unitary that I write on the global system and whatever work storage I take is energy preserving. So clearly, and this is something that we saw in the erasure thing yesterday as well, given that I go from one energy eigenstate to a superposition of eigenstates, my work storage is going to have to provide that energy difference. Yes, so I'm going to take now a work storage and try and do it with that. So yesterday, was it yesterday? Yeah, it was yesterday. We did the work storage, which is a continuous Hamiltonian, where essentially the Hamiltonian corresponding to a raising a weight. So today I'm going to take, because I only have a qubit and a discrete structure, I'm going to take a simpler version of that. I'm just going to take h of the weight is equal to the sum from n is equal to 0 to infinity of E n n. So this is actually just a harmonic oscillator. Okay, so harmonic oscillator, well, right. So it's a harmonic oscillator Hamiltonian, it's an infinite ladder, and I'm going to start with the wave function of the weight. It is going to be a broad support weight, so I'm going to say it starts from n is equal to n naught, and then it ends at n write that n naught plus L minus 1, and it's going to be n 1 over square root of L. So what I've done is, just like yesterday, I've taken the support of the wave function to have L states. So if this is my Hamiltonian, n is equal to 0, so on and so forth. It's basically a wave function that is some point here, it's a box, and then 0 the rest. And this support is L. Okay. So now I go, okay, I have that's my weight. This is the unitary I want to do. So what should the unitary look like? At this point, I consult my notes. Right. Okay. So now, how do I change this into an energy preserving unitary? So the only problem with the second state is that it doesn't have the same energy as the first state, but now I have a joint unitary. So I know what I want to do is I want to change 0 of the system, psi of the weight. And all I have to do is to change this into something that has the same energy as this state. So what can I do? I can do the following. If it stays 0, then it stays with psi weight. But if it goes to 1 of the system, then it simply goes to, I'm going to call it translation minus of energy on psi weight. So this is the translation operator, translation minus just by, well, okay, let me just say translation minus because it's a discrete thing. It simply takes space. Translation minus is the sum over n of n goes to n minus 1 in this. Okay. Yeah. It's not exactly the harmonic oscillator ladder operator because that involves some square roots of n's and n minus 1. So I'm just taking the translation operator quite literally here. Okay, right. So this is now if this state transformation is energy preserving, 0 psi weight has the same energy as 1 on the system and psi translated downward by 1. And of course, I can complete this unitary by just, I simply have to take all of the other possible. So what was one system and psi weight go to? But that's just a mathematical exercise. I have now a valid unitary operation. So now we look at what the system becomes at the end of this. So rho system weight prime at the end of this. So I start with 0 psi weight. I go into that. So I'm going to write down the density matrix now of this. And what I'm going to get, so corresponding to the 0, 0 term, I'm going to get psi of the weight. Corresponding to the 0, 1 term, I'm going to get psi of the weight, psi with a gamma plus. Corresponding to the 1, 0 term, I'm going to get gamma minus psi of the weight, and corresponding to the other one, gamma minus psi gamma plus. Okay. So this is just, I've taken the state, I've taken its Hermitian conjugate. Remember the Hermitian conjugate of psi minus is going to be psi plus, and then I've just written down the whole thing. Sorry if this is, okay, let me expand this a little bit because it's a bit cramped. Psi gamma plus, psi gamma plus. All right, export. So in some sense, what I'm doing here corresponds to what I claimed in yesterday's class about if you take a weight that is broad enough, then you in fact see that it has the properties, that the final state has the properties that you like. But now we're doing it explicitly. Okay, now I haven't yet proven that I've done the transformation I wanted, because of course psi system is now correlated with the weight. So now we want to say, what is the, let's say, what is the probability that I get psi system in 0? So I wanted to change psi system from 0 to the state plus. So if this succeeds with, well, full success probability, then I would expect that if I make a measurement of the system in the plus minus spaces, then I would get the plus state. So all I have to do now is to check what is the probability of psi system is equal to the plus state. This is just a standard quantum measurement. I do trace of phi plus on the system, tensor identity on the weight, because I do not care what the state of the weight is, on rho system weight prime. Did I write prime there? Yes, in a very weird place, but I did. Okay. And the projector on psi plus, of course, this projector here is, as a density matrix, is just 1, 1, 1, 1. And so I can do this calculation. I'm not going to do it in full quantity, but full generality, it becomes so equal to, oh, okay, let me 1/4 times 2 plus psi m plus psi m plus psi m gamma minus psi m. Okay. Right, so this is the answer that I get. I want this, of course, to be 1, but this now depends on these two. And these two things are very easy to calculate. Oh. This is the overlap between the, oh, not m, sorry, that was w. Oh, I wrote m. This is the overlap between the state of the weight as it is first and the state of the weight when it's shifted by one amount. That's very simple to calculate. If you have L states, then when you shift it by 1, all of the L states will contribute to the overlap except for one of them. So you're going to get 1/4, 2 times plus, and this is going to be 1 minus 1/L plus 1 minus 1/L. And this is going to be now 1 minus 1/2L. Okay. So this concludes essentially the argument for why what I talked about yesterday, but as well what I talked about here, why it works. If you choose a system of a weight that is a broad coherent state, then you are assured that even when you shift the energy of the state by a little amount, as long as that amount is much less than the width of the state, you are guaranteed that your you could somehow look at the system and the weight separately, and it looks like you've just done a unitary on the system. So it is important that you have correlated the system with the weight, but as long as the weight is broad enough and coherent enough, that correlation is very small. So you could also do something similar and look at the state of the weight. It's going to be essentially a mixture of states that are very close to each other. So that will also be quite close to the original state of the weight. And so the two things that were needed here. So one of the things is, so the broad coherent state. And so the meaning of the term broad is essentially much larger than the shifts in energy. So if I was to use this for 10 unitaries, then I could possibly maybe shift it 10 times. So I need it to be much broader than 10 units, for example. And the second thing, which I haven't discussed here, but it is actually important, is that it is much higher than the ground state. Why is this the case? Well, everything that I just did, including this calculation where I calculated the overlap, it assumed that I could actually translate it up and down. But of course, if I am close to the bottom of the ladder, I cannot actually translate the state that is in the ground state downward anymore. So there's going to be an additional error that's introduced, which means that actually I will not be able to do the unitary that I want to. So if you combine these two things, what it means that you need to start in a state that is already high enough, and you need to stay higher than the ground state. So even if your state is broad enough, at some point, because of all of the shifts, if you have a probability of being in the ground state, you will have to pump more energy into this weight to lift it off the ground state, so it still has a space below it. Okay. And so now when you use this work and you take a good enough work source, you can essentially prove two statements that are sort of not the opposite of each other, but they encode two things. One is that statement A is that given any rho and a unitary, so given any system that I want to do and a unitary on the system, as long as these are finite dimensional and the energy involved is finite, one can find a weight, so a state of the weight, and a unitary that acts on system and weight. Remember, this is energy preserving. Right? Such that, so U rho S U dagger S, so this is the state that you wanted, minus the state that you actually get, which is trace over the weight of U S weight, rho S tensor, rho weight, U S weight dagger is less than epsilon or any, so I should say, okay, given any this, and so rho S, US, and an epsilon. So I give you rho S, I give you a system, I give you a unitary I want to do, I give you an allowed error. You can find a state of the weight and an energy preserving unitary on both of them such that you are within that error. Okay, but the second statement, and this is important as well, I'm going to squeeze it here, I'll write it in blue so that it's clear, is that if I give you, given a rho weight, so I give you one of such state of the weight, the problem is that once I fix the weight, no matter how high in energy it is, no matter how broad it is, I can also always find, so one can find a rho system, a unitary on the system, and an epsilon such that this is impossible. So such that this unitary, such that US is impossible, even within epsilon. Okay. So it's a combination of two things. If I fix the system, I just have to choose a good enough weight. But of course, given any weight that I choose, given any weight that I choose, I can always find a system that will be the shift or the unitary will require shift in energy that is too large. Or maybe I have many systems in a row and then the total unitary that I do is actually way too complicated and will require a shift that hits the ground state or will shift the state of the weight out of its support. All right. Is there any question? None? Okay, then since I used up 6 minutes extra last time, and since I finished with this topic for today, I think I will conclude here. The next topic will be a little bit of a shift. So far, everything that we've been doing has discrete operations. I do a unitary, I might reset with the thermal bath, I do another unitary, I discuss all of the things we can do with this. In the next lecture, we will discuss autonomous quantum thermal machines, which essentially are continuous machines. So rather than doing discrete operations, I will write down what is called a master equation or a Lambdadian that governs the continuous evolution of the system. And so every one of the discrete operations will be replaced by an interaction. So rather than reset with the thermal bath, I will discuss how we write a continuous thermalization model. And rather than doing discrete unitary operations, I will discuss how we can write down Hamiltonian interactions that mimic these or lead to these unitary operations. Perfect. Thank you. That will be all.